provide you with the standard potentials. I did not provide you right now. Sorry, it was a lot of papers to print already. So I'll show you, we will discuss it. So guys, how do you decide what's going on? You have a cell. Ooh. I hope it will not move like crazy and will not be fuzzy. Okay, so you see that this is a cathode, cathodic side. On cathode, we always have reduction. This is the anodic side. On the anode, we have an oxidation. So our cathode is iron. It can be just a piece of metal that is conductive. We need to look for two elements, or for the same element in two different oxidation states. What do we have? We have iron and iron 2+. So we know iron 2+ will be reduced to iron. We could have iron here and two different elements, or let's say the same element in two different oxidation states. We would know that that iron was just a conductor, okay? And whatever we had in different oxidation states would be reduced. Like the homework you had a carbon electrode. Carbon can be conductive and had, I don't remember what it had, two different species. Maybe iron 3+ and iron 2+ in the solution. Okay? So you know carbon has nothing to do. It's just a simple conductor. Okay? It brings electrons for reduction. That's it. And what I would write, it's not this case, it's a different case. Okay? I would write iron 3+ would be reduced to iron 2+. Can you see? And carbon is just a piece of something that will bring those electrons in.
And the homework is chlorine.
Chlorine, yes, that's
I
right.
skipped that one. I had no idea. I was like, this is stupid.
Did you figure out?
No. I just skipped it and moved on. I was like, oh,
No,
okay.
no, okay. For your homework, it was Cl- and
Because it just had
Cl2.
carbon in it. I was like, this isn't even part of the cell. Like, what am I supposed to do with this carbon?
Yes,
that's
let's
in here?
talk about it now. I'll just give you what's happening. You're
like,
looking
how's-
for the
how's
same
chlorine
element.
doing?
Chlorine is here, but it's in different oxidation states. -1 and 0.
Yeah.
That's what will be reduced. So what can be reduced? Can Cl- be reduced? No, it's already
Sorry.
reduced. So it will be Cl2 plus 2 electrons goes to Cl-, and we need 2 of them. That's what will be reduced.
Okay.
Okay? Piece of carbon is just to bring electrons in. That's it. Okay, I already gave you one part of that question, but hopefully you can see how that works. Okay? All right. We don't have that complexity here. We just have iron 2+ and iron. So you know, we need to look for this kind of reduction. Right? And this is cathode, where we will have a reduction. And this is an anode, where we will have an oxidation. So I need to look for the standard potential of iron 2 to be reduced to iron metal. So if you look at potentials, I don't know if you can see, there is one case that says iron 2+ plus 2 electrons goes to iron solid. So please pick that one up out of all other possibilities. It comes from your textbook, okay? So standard potential is -0.44 volts. All right? The second, so far we are good? Okay? The second one, anodic side. We know it will be an oxidation, but we will use reduction potentials. That's why we will write it as a reduction. So copper will be oxidized to copper, 2+, right? But we will write it as a reduction. So copper 2+ plus 2 electrons will go to copper solid. And I need the standard potential for that. So let's see. I have again a table with all kinds of reduction potentials. Copper 1 reduction is not good, but copper 2 reduction is exactly what I need. So it's 0.339 volts. So the first one is cathodic process, the second one will be on the anode. Okay, cool. Now, it doesn't ask to write the cell reaction. Does it say for the cell? The extended. Okay, that's the only thing it asks to do. So that's what you do. But if I ask you about the cell process, what would you do? Look that we have exactly the right number of electrons. That's good. Subtract the anodic process from the cathodic. So cell reaction would be iron 2+ plus copper solid goes to iron 0 plus copper 2+. Okay, good. What is reducing, guys? That's good. Cathodic process is where we have reduction. Anodic process is where we have oxidation. So copper was oxidized. That's good. Okay, if we had standard conditions, everywhere we would have 1 mole of solutions or 1 bar pressure if we had gases. Then potential for the cell would be just standard potential at cathode minus standard potential at anode. But we do not have standard conditions. So whenever I say calculate the cell potential, it means I want you to use the Nernst equation, okay? So potential at cathode will be our standard potential at cathode minus 0.0592 divided by 2 electrons, because that's how many are involved, times log of 1 divided by concentration of iron 2+. Okay, let's put the numbers in and find it. Negative 0.44 volts minus 0.0592 divided by 2 times log of 1 divided by iron concentration. What would be iron 2+ concentration?
0.05.
It's 0.050. It's a soluble salt. Any nitrate is soluble. I gave you the concentration. It means it's completely dissociated. Okay, so what is it? I have negative 0.4785. Okay, I do a very similar setup for anodic potential. So you can see I corrected my standards with the conditions we had. It's, slightly different. And we do the same thing for the anodic process. We look at the reaction whenever it's written as a reduction, okay? So standard potential for the anode minus 0.0592 divided by 2 times log of 1 divided by copper 2+ concentration. So the standard potential was positive 339 minus 0.0592 divided by 2 times log What do we have for copper concentration?
0.02.
Yes. And guys, do you see why I put 1 on top? We are talking about standard states. Those two are in standard states. They cancel itself. That's why numerator has 1. Okay, and for that, I have 0.2887. So I corrected the conditions in my anodic half cell, or I used the conditions, and I corrected the standard potential for those conditions. And finally, the cell potential will be potential at cathode minus potential at anode. So negative 0.4785 minus 0.2887. I got negative 0.767. And you can round just to 2 suffix because we will limit it up here. The reduction potential for iron only had 2 suffix. Okay, all right. I did not ask here, but I could. What kind of reaction or cell is this? Is it electrolytic cell? Is it voltaic cell? Is it spontaneous reaction? Is it non-spontaneous reaction? What would you say?
It's voltaic cell and it's spontaneous.
Is it spontaneous?
Because E is negative, that makes delta G negative, right? No?
It's exactly opposite. Okay, delta G is negative NFE. N cannot be negative. It's number of electrons. F cannot be negative. It's Faraday's constant. But E can be negative or positive. So negative E makes delta G positive. So now, let's answer now. Is it electrolytic cell with non-spontaneous or voltaic with spontaneous?
It would be electrolytic. Non-spontaneous.
It's non-spontaneous process. If you just let it go by itself, you are not forcing any reaction. Those two would prefer to be exactly opposite. Whatever we had as a cathode would prefer to be an anode. And whatever we had as an anode would prefer to be a cathode. We can force that reaction. Like we can just force it, but it's not spontaneous process. Questions?
You said it was electrolytic?
Electrolytic.
And it's non-spontaneous?
Non-spontaneous.
Isn't that why it doesn't work?
Yes, because the cell potential is negative. Delta G is positive. Yes.
So electrolytic can only be non-spontaneous and voltaic can only be spontaneous?
Yes.
So could you say that for this reaction to happen the way that it's set up, you would have to add that many volts of like,
You have to apply, usually even more, to force it.
okay.
Good? Yes.
When I was doing the homework,
Yes.
I just used the next equation for the,
Whole
Yes.
cell. You can do it.
okay.
You can.
So does that mean that you would switch?
Yes. They would do exactly opposite. If you just let it do whatever it wants without forcing, then iron would like to oxidize by itself comparing to copper that would like to reduce. Even look here, you know, electrons always prefer to go to more positive potential. So this reaction is easier to be a reduction, and that is much easier as an oxidation, right? But like you can do it, it's just, you just need to put work in. All right, other questions?
So if you were to do the nurse equation for the cell reaction, would
Yep.
it switch like the products and the reactants for?
Like what you would do, like guys, I don't want to confuse people. If you can do whatever I ask you, it's good. But You can find the standard cell potential, standard potential at cathode minus standard potential at anode. And you can say cell potential is standard cell potential minus 0.0592 divided by how many electrons altogether? 2 log and have Q up here for this reaction.
Okay.
Okay?
Can you give the same answer?
Yes.
Okay.
Good. Yeah.
Yeah, it's the same, okay.
Anything else? Okay, good. We are moving.